Okay, good afternoon, everybody here. Actually, welcome back to the AI talk series. Actually, we introduced this year for, actually two talks we already did, and this is our third talk within actually this AI talk series. The talk of today is about extending traditional robust control methods for verification and validation of non-traditional controllers. The talk is given by Professor Pete Zeller. He's an associate professor in electrical engineering and computer science at the University of Michigan. He is an IEEE fellow. He's also the recipient of the Hugo Schuck Award in 2003, the Brockett Williams Outstanding Paper Award in 2020, and NSF Career Award in 2021. His research focuses on robust control theory, which addresses the impact of model uncertainties or uncertainty on systems design. He has been a contributor to the Robust Control Toolbox in MATLAB since 2001. He was a principal scientist from 2004 to 2008 in the Aerospace Electronic Systems Group and at the Honeywell Labs. During that time, he worked on the redundancy management system for the Boeing 787, sensor fusion algorithms for automotive active safety system, and re-entry flight control laws for NASA's Orion vehicle. So welcome actually to Professor Pete. And actually, we are happy actually to have you here, Professor Pete Zeller, and the floor is yours to start the presentation. So we'll ask the audience, the attendees, to leave the questions at the end of the session, at the end of the talk. And if you are happy, please put your questions in the chat, and we'll take them after the talk, and we will ask the question actually on your behalf to Professor Pete Zeller. Thank you very much. So Pete, the floor is yours, as I said.
Excellent. Thank you for the nice introduction, and thanks for inviting me to give this virtual seminar. I'll say I come from a model-based background, and so the talk will start with maybe some model-based methods for flight controls, and that'll kind of set the stage for how are things traditionally done, and maybe that'll expose some of the challenges as we move towards non-traditional controllers, things like neural networks in the loop or online convex optimization, adaptive controllers, things of that nature. So let's jump in. I'm going to start by talking about control of flexible aircraft, and I'll explain why you would want a flexible aircraft. What are the benefits? Then I'll talk about how we analyze these things in a traditional fashion, and then that'll feed into non-traditional controllers, and then we'll kind of wrap up at the end. So let's jump in. Control of flexible aircraft. So what's the point here? If you want to make an aircraft more fuel efficient, there's a range equation that tells you how does the range relate to airspeed, engine efficiency, lift over drag, and then your mass at takeoff over landing. And so the point of this equation is that if you want to improve engine efficiency, there's only a few kind of basic engineering design knobs you can play with. You can make the engine more efficient. You can make the lift to drag ratio higher. And the way you do that is make longer, more slender wings. Like on a glider, it's more fuel efficient or more, flight efficient than on a fighter aircraft, which has kind of short, stubby wings. Or you can reduce the mass. So you can take weight out of the wings, make them lighter, and then you get an efficiency benefit. Now, I'm not going to worry about the engine efficiency. I'll focus on the last two. Take weight out of the wings, so make them lighter, and make the wings longer, more slender. By doing that, though, you make the wings kind of more flexible. So you're increasing the coupling of the structural dynamics in the rigid body motion. The structural flexibilities come down to a lower frequency. You also increase the coupling with the aerodynamic loads and the structural deformation. And then there's something called a flutter margin, which is the speed at which you can fly the aircraft. The flutter speed is the speed at which if you fly too fast, the aircraft will basically kind of disintegrate in flight. These vibrations will basically cause the aircraft to catastrophically fail. So aircraft that you fly in, commercial aircraft, have a flutter margin. You compute the flutter speed, and then you have to fly a certain fraction below that. So just to kind of put this into context, here's an old NASA video that, this is showing flutter on the horizontal tail of the aircraft. and they were doing experiments, and you can kind of see this coupling between the structure and the aerodynamics, and you can tell, if you allow these vibrations to grow, that structure will destroy itself, and kind of it ends with disaster. This is what we want to talk about. Now, within the last 10 or 15 years, there's been a lot of different flight demonstrators. Lockheed Martin built 7 of these, what they call body freedom flutter. You can kind of see the slits in the wing to make them more flexible. And they were trying to study how can we use controls to make things look stiffer than they are. So you've got wings that are longer, more slender, less weight. They start to vibrate. And if they're vibrating up and down, you can use the trailing edge surfaces. You can see them here. These would be the ailerons on a traditional aircraft. You can use those to create forces that'll make the wings look stiffer than they are from the structure alone. And you can use feedback then to damp out these vibrations. So they built 7 of these. 6 of them were destroyed during their flight test, and they gave the 7th one to the University of Minnesota. That's shown here. That's my colleague Gary Ballas, and this is me, a long time ago. So that started us on this path of looking at these flexible aircraft. There's been a number of other projects. This one's from the EU, led by a project with Ballon Vanek, the FlexOp program. They've had a couple other programs to look at this. This is a more recent NASA vehicle, the X-56A. This will come up in a moment. And Lockheed Martin has obviously also played a role kind of in both this aircraft and this aircraft, along with the Air Force Research Lab. So our project on this was called POW, Performance Adaptive Aeroelastic Wing. So this was done when I was at Minnesota, so maybe a little more than 5 years ago now. We had 2 research aircraft. The first one, which is shown on the left, is a 10-foot wingspan, 14 pounds. It was a scanned replica of that body freedom flutter aircraft from Lockheed Martin. And then we had a second aircraft, which was this, what we called MA Wing 2. It's a 14-foot wingspan. This is a half-scale version of that X-56A, the more recent NASA aircraft. And so the goal here is to suppress flutter, control the wing shape, and try to optimize performance, get things that are more fuel efficient. So I'm going to describe this from a model-based point of view, and hopefully this will kind of highlight some of the challenges with doing data-driven or learning-based methods. So just to kind of tell you maybe the configuration, this is a cutaway of the MA Wing 1, the first aircraft. That was the main one that we flew. You can tell on each side there's what we call a body flap and then 3 flaps on the wing. So those are labeled on the left and right, L1 and R1 and so on. So the outermost ones are L4, R4. And then there's lots of sensors on the aircraft, especially in the center. But the ones we use for this vibration suppression are accelerometers on the fore and aft of the wingtips and accelerometers in the body. And those are useful because you can then sense how much the wings are vibrating relative to the center body. Now, as I mentioned, a lot of this was done at the time and still is model-based. And so modeling is actually fairly challenging here. And so maybe this gives you some insights of where, data-driven techniques can come in. And the reason it's challenging is because you have to model the aerodynamics, the structure of the aircraft. You have just kind of the rigid body dynamics of the aircraft, the standard kind of Newton-Euler equations. And then the feedback controller has its own dynamics. And so there's a range of models here. There are really high fidelity models. That was done on our project by CMSoft. These are the type of models that are like computational fluid structure dynamic models. You run them on a supercomputing cluster. These are maybe our highest fidelity models. Then we had Nastran models from Virginia Tech, reduced order models from Data. That was taking CMSoft's models, collect some data, and construct reduced order models with STI. That was another company on our project. We had kind of medium fidelity models. These are called panel code models, where you kind of grid up the aircraft into little small kind of plates or little chunks. And each plate basically has a simple model of its kind of motion and the aerodynamics. And then the models that we use for the control design were very simplified. I'll show these in a minute, but these are like 10 to 12 state models collected through some amount of physics and some amount of corrections through data. So let me tell you, maybe if I back up one slide, I'm going to focus on this low order model. This is what we call a control oriented model. Very simple, but good enough for us to do our control designs. So how did we construct that? Well, we started with this Nastran model that I mentioned from Virginia Tech. That's like a beam and rod type model. This is kind of showing the layout. So it's a very kind of simple finite element model. unsteady aerodynamics with a doublet lattice technique. In the initial model, you need some data for what are the structural parameters in this. We had a CAD model for our aircraft, and we did some very simple static tests. We take a wing and just put a weight on it, and that would give us some crude estimates for the structural parameters for this. Then we also did ground vibration tests. So this is the aircraft here. It's hanging from a spring. So that's supposed to kind of mimic the free flight conditions, although there's no aerodynamics here. And then we took a little vibration, attach it through a stinger to the aircraft, and we just start shaking the aircraft. And we have accelerometers in many places over the wing. We collect data, and then we could build a linear time invariant model just of the structures. So, the data that we collected, if you take I think we had 20 accelerometers. They're kind of in this kind of black grid. The black grid is the aircraft in its undeformed position. You start shaking it, and then you collect all the accelerometers measurements. You map it to the frequency domain, and then you sum and square all those measurements. You get this plot of singular values versus frequency. Wherever there's a peak is like a vibrational mode of the aircraft. The aircraft is really getting excited if you shake it at that frequency. So that, for example, this first structural mode at that frequency, this is how the aircraft is vibrating. It's kind of like a bird flapping its wings up and down. One thing to note is that's at a pretty high frequency, at least for controls. It's about 33 radians per second here, which is about 5.5 hertz. That'll become important in a moment. And then you have more bending modes as you go to higher frequencies. So the first three bending modes, this is the first one. The gray is a picture of the aircraft in its undeformed state. The red is how does the aircraft look when it's bent at its maximal position in this vibration mode. So the first bending mode, the aircraft's kind of flapping its wings, and this is with the wings kind of in its downward configuration. The second bending mode, the wing is kind of twisting around its lengthwise. It's a torsion mode. And then the next bending mode kind of has kind of even more kind of higher order kind of shape to it. So these first three bending modes are the most important for the controls. So these were kind of built into our low order model. So we basically take the ground vibration data, that's all test data, use it to update our physics model, this Nastran model. Then we extract these kind of mode shapes and modal frequencies from that Nastran model. And then Dave Schmidt, who was on our project, he constructed a low order flight dynamics model. That looks like the following. It's got 4 rigid body states. It's a purely longitudinal aircraft model. So if the aircraft was rigid, you'd have like the forward velocity, angle of attack, which is the angle between the incoming wind speed and the center body of the aircraft, the pitch angle, and the pitch rate. Now we add 6 more states. These are capturing the first 3 elastic modes. So we have just a 10-state model. And it's in this kind of linear time invariant format. The only unique thing here is it's what we would call parameter varying. It depends on the airspeed. So as the aircraft goes faster and faster, the poles and the dynamics change, and you'll see that. And in fact, what happens is at low airspeeds, the rigid dynamics are kind of dominating. As you go to higher airspeeds, the flexibilities become more important. And in fact, those flexible modes coupling with the aerodynamics can become unstable. So the poles of this move into the right half plane as you go to higher airspeeds. So this is a model that's collected from a mixture of physics and data that's collected on the ground. We then went to flight test data. So our model is kind of blue after the flight test data, and then the flight test data is very noisy. So this is maybe another point about the data collection. It's relatively easy to collect data on the ground, like the ground vibration data. We could collect lots of that data if we wanted to. Flight test data is very expensive. Even for us, we would collect snippets of 30 to 60 seconds of flight data. And so then when you map that to the frequency domain, so this is frequency, and then this is from collective L3R3s. If you move the L3R3 surfaces together, how does that change the accelerometer in the rear of the center body? This is from the L4R4. Those are the furthermost outboard flaps. If you move those collectively together, how does it affect the center body accelerometers? And so the data is very noisy because it's very limited quantity of data. But you can see it kind of matches our model fairly well, or at least we were happy enough with that to go ahead with the control design. Now, the other piece of the control design is this is just modeling the airframe. So what happens when you start moving these flaps? How do the accelerometers move? Now, there's all sorts of other dynamics in the loop. We are measuring accelerometers, angular rates. Those sensors have their own dynamics. The flight control computers have their own, time delays associated with them. There's actuators, which are relatively cheap hobby grade servos on this aircraft. Those have little time delays and, that low pass dynamics as well. All of that's important because for controls, we're controlling at a relatively high frequency. The first bending modes add about 30 radians per second. So any small time delays or extra dynamics are actually going to have a pretty strong influence on the feedback control. So this is just showing all these extra components, how much phase is lost as a function of frequency. And there's 72 degrees of phase loss where at the frequency of that first bending mode. That's actually a lot of phase loss in the control domain. Usually we think about having 60 degrees of phase margin, 45 degrees of phase margin. Those would be typical numbers. So an extra 72 degrees of phase loss, if you didn't model this, could cause the closed loop to go unstable. So we modeled all of these components as well. Some of these were modeled, by collecting data, on, for example, the dynamics of the actuator. So again, it's a mixture of data collection, but also physics-based modeling. Now, just to show you what happens in flight with no control, we're flying along here. We go into a dive, we go up in speed, and what you're going to see is at some point the speed gets too high. We're beyond the flutter speed. Our models, we had a bunch of different models. They all predicted that the flutter speed, the speed at which the aircraft would kind of break apart, I can show this one more time, was around 30 meters per second. And in the flight test, that's actually what occurred. The aircraft broke apart around 30 meters per second. So that again gave us confidence in our models. And so you're kind of just seeing the aircraft starts vibrating. This video is kind of from the center body. It's a camera looking out at the wings. And we've got kind of QR codes here we can use to reconstruct the vibrational motion. That we didn't use for real-time control because the image processing at the time wasn't fast enough to run in real time. But we could use that data after the fact to try to understand what was happening. This is just showing the highest fidelity model that we had from CMSoft. They built the reduced order model. They get the first order bending mode out of it. This is kind of what the motion of the bending looks like. This is what happens in flight, and you're kind of seeing the center body pitch back and forth, and it kind of matches qualitatively this kind of motion that we were seeing from our models. Again, it's just giving us confidence that our models were accurate, given that we had such a limited amount of flight data. Now, what we wanted to do at this point was be able to fly beyond this flutter speed. This is all without a control yet. We want to design a controller then that will damp out this vibration and be able to fly faster. And the control is making the aircraft seem more stiff than it really is just through feedback. So here are the control objectives. We want to add damping. So as we get close to the flutter speed, hopefully we're damping out these vibrations. We need to remain within the actuator limits. The actuator can only move so far, and it can only move within a certain rate. There's another pilot, there's an autopilot that's doing just basic longitudinal motion, change the altitude or change the pitch angle and so on. So this is acting at a low frequency. We don't want to interact with that at all. We want to just be damping out these high frequency vibrations. And then there's a lot of model uncertainty here. So this is the piece that I'll talk about in the second half, which is how do we deal with these type of model uncertainties in non-traditional controllers. So we had several different control techniques. The one that I'll talk about is an optimal control technique, from the robust control literature, H-infinity control. I won't dwell on that, but our controller was designed to use L4R4 flaps and then the L1R1 flaps. So those combinations together can kind of be used to reduce the vibration. So we designed 3 controllers. Ours was this H-infinity controller. There were 2 more controllers designed on the project. One of them was just a classical controller, and they were designed to just first increase the damping at a low airspeed. The flutter speed is 30 meters per second, so this is well below that airspeed. But we want to just see, can we get close to the flutter speed without destroying the aircraft? So I'll show you some flight test results, and here are some references after the fact if you're interested. So this is a plot of the poles, the imaginary part versus the real part. Notice the imaginary part is starting at 25. So I'm not showing the low frequency poles, and I'm only showing you the positive half of the complex plane. So the three main kind of loci that you should be interested in, there's three bending modes that I'm going to focus on. The first bending mode, this is actually an open loop and closed loop. And then here's the second aeroelastic mode. It's actually an open and closed loop. But let's focus on the first aeroelastic mode. In open loop, as you go up in airspeed, the pole follows this trajectory. And if you go fast enough, the pole moves into the right half plane. So here's the vertical line. In the right half plane to this right side of the vertical line, the system's unstable, and that's where the aircraft will basically disintegrate in flight. It'll basically catastrophically destroy itself. On this side, it's stable. So at low air speeds, everything's stable. The vibrations aren't growing out of control. And over here, they go unstable. Now, when you add the closed loop, our models predict that the path will kind of go further into the left half plane. It'll eventually come into the right half plane, but at a higher airspeed. So this is showing that we're adding damping. We're pushing these poles further into the right half plane. And this is actually from the flight data with the closed loop. So you're seeing kind of a reasonable match. The three diamonds are from our flight test data. You don't see much impact on the second aeroelastic mode, and that's just because our controller was designed really to focus on this first aeroelastic mode. This second aeroelastic mode isn't the one that's going unstable. This is another plot of the same kind of result, but basically it's showing damping or how far you are from the right half plane versus velocity. In this plot, negative means you're stable, positive means you're unstable. All these flight tests were done, at least for the H infinity controller. We ran, this is, I guess the red dots are open loop. So you see when we crossed the line of 0, that's where we went unstable. That happened at this open loop flutter speed, which is, just above 30 meters per second. Here were all the controllers that we tested, and you can see we were able to fly beyond the open loop flutter speed, and we made a prediction of where the closed loop flutter speed is, and it's at some higher speed. We ended up not testing the H infinity controller at higher speeds. That was more to our flight test program. The program ended when we tested these two. We were going to do a third round where we tested all three at a much higher airspeed, but the program concluded before we did that. But this is, again, just showing we can fly beyond the flutter speed through the use of control. But we had to do a lot of modeling to get to this point. Again, we collected data. And so then there's a question of, each aircraft that we built. I'm showing you results that actually spanned kind of multiple different aircraft that we built. Every aircraft that we built, we went through this lengthy modeling process that involved physics and data collection. It would be nice to know, can some of this process be sped up with, more AI or machine learning techniques? So this will now feed into the next part, which is I'm going to describe to you, why model-based methods are so common currently in aerospace, which is not only does it have to work, there are requirements, in the US to certify an aircraft, you certify it with the FAA. In Europe, you would be doing that with EASA. So there's all sorts of requirements to prove not only does your control algorithm work, it actually works in the presence of some amount of model uncertainty. So like in a traditional undergraduate control class, we might talk about things like gain and phase margins. Those are like really simple metrics to try to understand if my model that I use for control design was off, either in gain or phase, I need to show that the controller is still going to work. And those simple metrics are actually built into the flight certification process. You can find requirements on gain and phase margins for flight controllers. So the point is you need models in order to make those type of assessments. And so I'm going to talk about, at a theoretical level, how are some of these things done? And the way I'm going to describe it here will then feed into maybe a method for how you could do this for non-traditional controllers. So let me start with just a very basic feedback loop. I have a plant, and I'll describe this in discrete time just to keep things simple. I have a controller. There's some reference signal I'm trying to track, and I've got some measurement. Let's just say everything's one-dimensional for now. Everything's in discrete time. And so let's say the closed loop, the reference is coming in, and then there's some state that's, involves the plant state and the controller state. I'll say those are stacked together, and I've got some sort of state space model for this. I won't worry about the Y for a moment. So one simple condition to prove that this is stable is to find what's called a Lyapunov function. So some function of the state, which is positive definite, And I want to show, you can think of this as like being energy. I want to show that the energy or the Lyapunov function at some time k is smaller at the next time k plus 1 by a factor of rho. So that's kind of what's encoded in this inequality. And the rho is less than 1, just saying that the energy is going down. And if you can show that, then what must be happening is x must be going towards 0, which will then be a proof of stability. And so then again, what's happening is the energy at time 0 goes down by a factor of rho at time 1, and so on at time 2, it's getting even smaller. And so you're getting a factor of rho squared from the initial energy to time 2, and so on. It's just getting smaller and smaller. So not only are you proving stability, you're getting sort of exponential or geometric convergence in free time. So then the state must be going to 0. Now, it turns out this has got a nice numerical implementation. This is related to a convex optimization. So now let's assume that this function that I'm talking about is a quadratic function of the state. The matrix in the center is positive definite. Then this condition, then you can kind of rewrite it in terms of P. That'll turn out to just be a positive, or a negative semi-definite condition on this matrix. And that's got a nice optimization that you can solve. Okay. So now I'm going to talk about what happens if there's some elements of, uncertainty or nonlinearities. So let's take the same feedback loop, but let's put a nonlinearity in between the plant and the controller. Now, this could model things like actuator saturation or rate limits, things that I haven't captured in these simple linear time invariant models. So if I call the input V and the output W, think of this phi as just a function. I'm showing the graph here. W, the output versus the input V, maybe it has some shape like this. That would be an example. Now, this closed loop is modeled. If I neglect the reference I just focus on the closed loop with a 0 reference. There's some state space model for the G and the K. V and W are the inputs and outputs of phi, so that's captured here. And then W is somehow feeding back into these linear dynamics, and V is coming back out. So think of this as there's a linear time invariant dynamics. That's easy to understand, interconnected with this nonlinearity, and that's maybe the piece that we don't understand how it's going to impact the closed loop. So I'm going to give you a simple condition for stability of this. This condition goes back to the 50s. But it turns out this condition can be adapted to try to understand things like neural networks, which is kind of one reason why I'm showing this to you. So let's make some assumptions about this. This is nonlinear, but let's assume it lies between a line of slope alpha and a line of slope beta. Let's say I don't know exactly what this function is, but it lies in the kind of white area. It doesn't cross the shaded area. Now that graphical condition can be written as kind of this quadratic inequality. So W is always, either bigger than alpha V and less than beta V. That's over here, or vice versa. That's all this kind of quadratic constraint says. And if I want, I can kind of stack this up and rewrite that same constraint like this. These two are exactly the same. This is just written in a different form. So this leads to something called the circle criterion, which is, suppose I want to show to you that the Lyapunov function is decaying on the dynamics of G and K. And all I tell you is that the nonlinearity here satisfies that quadratic constraint on the previous slide. Well, a simple condition is written here. I want V to be negative for any values of W and V where this term here is greater than or equal to 0. There's a minus sign. If you can find a matrix P that satisfies this condition, you'll have a Lyapunov condition. And the reason why is I don't know exactly what this nonlinearity is, but I know that this quadratic form here is a non-negative number. Let's assume lambda is also non-negative. I've got a negative sign here. So everything on the right-hand side will be less than or equal to 0, and I'll be back to our Lyapunov condition. So the point of all this, I went through the details quickly, is I can kind of adapt these Lyapunov conditions to problems where there's nonlinearities. Again, I can convert this into a semi-definite program, so I'll kind of skip the details, but you get to a matrix inequality where it's convex in the variables that you're searching for. I'll kind of skip through this in the interest of time. There are richer versions of this, which I'll just mention that if I know more than just kind of these sector bounds, the fact that the nonlinearity lines between two lines, if I also tell you there's slope bounds, like I tell you there's a constraint on the slope between any 2 points, there's more of these quadratic constraints that I can write. So this is just to tell you that, a lot of these ideas that I'm telling you can be adapted and be kind of made much richer. Okay, one last thing is to tell you about unmodeled dynamics. And so this last thing I want to emphasize is, I mentioned that we have model error, and the model error that we have is what's called non-parametric. And so what that means is we're thinking about our models as being like low order models, 8 or 10 states. The real dynamics are like partial differential equations, right? The flow over a wing is modeled by Navier-Stokes equations, or the wing bending itself is modeled by a partial differential equation modeling the structure. So we need to have some way of bounding the difference between a very low order state space model and something that's in principle infinite dimensional. And so just to give you a flavor for how that's done, here's a simple hard disk drive that's typically used in like cloud storage. There's a motor here that moves this read write head back and forth across the storage medium. And you could then, from the input at the motor to where the tip of the read write head, you could just collect some data and map it to the frequency domain. And you get a plot of magnitude versus frequency and phase versus frequency. Think of frequency as being a time scale. Go up in frequency, it's faster dynamics, shorter time scales. As you go down in frequency, it's slower dynamics, longer time scales. And the gold is like a simple model, and the blue is collected from 50 different disk drives. This is experimental data. And the main takeaway I want you to take from this is at low frequencies, all the models tend to look similar. If you move slow enough, it's basically just a piece of metal that's being moved back and forth. It's very rigid. This is like Newton kind of dynamics, rigid body dynamics. If you go to high frequencies, though, there's all sorts of the metal actually bends a little bit. There's all sorts of things that are very difficult to capture and model. And most physical models have this behavior that at low frequencies, they're very similar. They can be modeled by very simple dynamics. At high orders, there's lots of variation, or high frequencies or high speeds. There's lots of variation. There's lots of part-to-part variation. So how are we going to capture this difference between a model like the gold one, which turns out to be like a 6-state model, and the experimental data? Well, the way we do that is we basically just almost like put a tube in the frequency domain. We say, here's our design model. That gold I'll call G naught. Everything else is captured by some error. So let's say this is one of the 50 blue ones. Let delta be the error, and you've got a frequency dependent bound. As I go up in frequencies, shorter time scales, this error bound gets bigger. And the way I'll model that is I'll model the actual dynamics as having two pieces, my low order part and my error. And if I'm moving things, my inputs are at low frequencies, this is going to be reasonably accurate. If I start moving the input too quickly, this is going to start playing a bigger role. That's just reflecting the fact that the error bound is going up in frequency. So now how can we prove stability for something like this? Well, we'll go back to our simple feedback loop. I've got the nominal model. I've got the model error. The way we're going to do this is we're going to separate out, for now, just for simplicity, I'll assume the norm bound here is less than 1 at all frequencies. That's just to make the proof a little simpler. It turns out now this closed loop is stable for any uncertainty you stick here. If you just take the transfer function or the dynamics from W to V, those are linear dynamics, if it's less than 1 at all frequencies. That's known as the small gain theorem. And again, you can check this with the Lyapunov condition. The point is, we now have a stability proof, even if the model dynamics that I'm using are off by some amount. It's hard for me to characterize the source of that uncertainty, but I can at least bound it in the frequency domain. Okay, so what's the summary here? We've got all sorts of model-based tools that go back to, I guess, even the 40s, which is this kind of circle criterion. Then in the 80s and 90s, there was lots of work, especially related to the space shuttle program in the US. Magretsky and Rancer were kind of develop a richer version of which I just described you, this kind of integral quadratic constraint kind of framework. All this generalizes to multi-input, multi-output systems, different types of uncertainty. But this is all assuming the core dynamics, the nominal dynamics, are linear time invariant. That's the basic setting. There are extensions, but that's the basic setting. And there's lots of software tools. MATLAB, has a software toolbox that they have. Onera has been developing tools over time. So a lot of this, there's tools that people can use to assess the impact of these types of uncertainties. I'll skip over the numerical algorithms because I want to spend the rest of the time talking about how do we adapt all these ideas now for non-traditional controllers. Okay, so what do I mean by non-traditional controllers? Up till now, I'm assuming the plant and the basic controller are linear time invariant. So classical controllers, things like loop shaping or PI controllers or state space observer state feedback controllers. But what if I want to design a neural network to control a plant? I'm giving some references. There's been a lot of work over the last few years other than these. Adaptive controllers. Again, there's a huge literature on adaptive control. This figures from some work by NASA testing some adaptive controllers for launch vehicles. Or I want to do things like real-time optimization. So this is, a picture from one of Bechet's papers. But, things like SpaceX where you launch a rocket, they're using real-time optimization to recover the rocket and kind of land back into place. So these would be things like model predictive control. These are all non-traditional controllers in the sense that we don't have the same set of tools to ask questions like, what happens if the model of the plant that I'm using is off in some ways, that's non-parametric. It's hard for me to describe the source of the uncertainty, but I want to be able to do the equivalent of things like gain and phase margins. I'm going to just focus on the first one, just to give you a flavor of how this can be done. So to make it simple, let's assume the plant is linear time invariant. That itself could be a neural network. That actually won't make things more difficult, but that'll just make the discussion now a little bit easier. Let's assume I can measure the state, and I've trained a controller, and I've got a neural network controller that's been trained using reinforcement learning or something else. Now, what's the format of this controller? The format is you take in the state, so that's the input for kind of layer 0, and then at every layer, you multiply the previous layer by some weights, you add some biases, you apply an activation function, you get the output of that layer, and you just keep iterating. And then the final control law is there's one final layer where you multiply by a weight matrix and you add some biases. So the question is, can you prove that this is stable? And then could you do things like, well, what's the gain and phase margin here? If I trained a neural network controller, can I do things, make provable guarantees about model uncertainty? So the method here is to first separate the things that are maybe easy to analyze from the things that are not so easy to analyze. So in the neural network, the weights and biases are all just linear operations. It's the activation functions where you have some nonlinearity. Those are things that are maybe difficult to understand. So usually we try to pull those out or extract the long list of activation functions. So think of these as being the vector of all the inputs to the activation functions at all the layers. These are all the outputs. We have the state coming into our neural network controller. We have the control command. And what's sitting up here are all the weights and biases. So N is just a big linear matrix. Now we need to bound the effect of the activation functions. So this sector constraint that I mentioned before, these alpha beta lines that you can create quadratic constraints, you can make local versions of that, and there are even richer versions of these quadratic constraints. But you can write out a bunch of quadratic constraints. I'm doing it for hyperbolic tangent, but for things like ReLU and so on, there are other quadratic constraints that you can write. Once you have those quadratic constraints, then this Lyapunov theory that I mentioned with the circle criterion can actually be adapted for this setting as well. It's more a notational problem now. You have lots of nonlinear elements, but you can write out Lyapunov functions. You've got these quadratic constraints on the activation functions, and you can get stability proofs. They're not global at this point. Usually you're getting kind of local regions of stability. If the state remains within a certain ellipsoid, I can prove I'll come back to the equilibrium point. But all that kind of goes through with some caveats that I'll mention in a moment. And importantly, if the plant had uncertainty, it turns out you can adapt this whole methodology to handle uncertainties in the plant, like non-parametric uncertainty, things like gain variations and phase variations. You could handle other actuator nonlinearities. And so at the end of the day, you could compute things like gain and phase margins for neural network-based controllers. Disk margins are a slight generalization that capture both gain and phase margins. So we have some recent papers on doing exactly that. I give you a neural network controller, and then you want to compute disk margins. And again, the point of all that is that gives you maybe a certification path in the either with the FAA or with EASA for aerospace controllers. Let me give you just a very simple example to show how this plays out. So just an academic example. I give you an inverted pendulum This is written in continuous time, but we discretized it with a 20 millisecond sample rate. There's sign terms here. So the trigonometric terms, we also bound those with sector constraints. We designed a very simple neural network. It's only 2 layers, 32 neurons per layer. So one of the caveats here is that while everything I mentioned can conceptually be generalized to many neurons, deep neural networks, fundamentally we're solving a convex optimization, a semi-definite programming problem to compute these stability proofs. Those are convex. They scale reasonably well for typical control design problems, but they don't scale to the level of being able to handle, millions or even billions of neurons, the type of structures you might see in things like large neural networks. They scale currently to maybe a few hundred neurons, maybe 1,000 neurons if you were to write specialized code. So that means to use the techniques I'm describing to you, you really need a small neural network to be able to do this. We're currently working on ways to like scale these methods up to much deeper, wider neural networks. Now, we're talking about real-time control. So fundamentally, even the real-time implementation will limit the number of neurons in the neural network that you can implement. But just to tell you, like, this is, I understand, a very small neural network, and that is a constraint. The 32 is even smaller than what can currently be handled. But just to give you some caveats about this. We set all the biases to 0. You can handle the biases. Those will end up just changing where the equilibrium point is. And for this example, we're using hyperbolic tangent as the activation function. So now this is going to show the phase plane. The inverted pendulum has 2 states, the angle of the pendulum and the rate. We are able to prove this circle here is a stable region for the neural network that we trained. I'm glossing over the details of training the neural network for control. That was kind of basic reinforcement learning. The paper that I mentioned by, on the first slide where I talked about non-traditional controllers, there's a paper by he and Murat Arkak and myself. It goes through these results in more detail. But we're able to prove that the neural network will definitely be stabilizing and bring you back to the equilibrium point if you start within this blue circle. So that's in kind of this top paper here, which is a TAC paper from several years ago. Now, I have a few minutes left, so I want to talk just maybe about some other kind of issues where these techniques can be used. And so I'll kind of jump to this using real-time optimization. And the piece I want to talk about real-time optimization is not necessarily the feedback piece, but when you do things like model predictive control and you're doing it in a real-time setting, you maybe are solving some optimization and you want to prove that optimization is going to converge in a certain amount of iterates. And then that proof then allows you to implement this in a certain sample time. So I want to just tell you some work. This is really, work that was led by Laurent Lessard and Andy Packard and Ben Recht, maybe 5 or 6 years ago. And the setting is, suppose I give you an optimization problem. I'm trying to optimize some function over n variables. Suppose I tell you the function is strongly convex, and it's got Lipschitz bounds of L. Now, you can use gradient descent to try to optimize this. That would be something like this. Every time you're at an iterate, compute the gradient of the function and step in the opposite direction with a step size of alpha. You can show that this is not the fastest converging algorithm, though. There are other algorithms like heavy ball and Nesterov's methods. These use what are called momentums. They store past history. So you can see there's an xk minus 1. So they're using past history to speed up the convergence. Now, the connection here is that all these algorithms, all 3, and there's other versions, they can all be written in this form where you've got some basic dynamics here, where gradient descent, this would be a first order dynamics, interacting with a gradient, and then the gradient's telling you how to update for the next iterate. And the work that I mentioned from Laurent and Ben Recht and Andy Packard basically use this decomposition. This is very similar to the decomposition that we used to analyze control systems that have uncertainty or nonlinearities. I've got linear time invariant dynamics. I've got a gradient, which is a nonlinear function. It turns out that the assumptions, the Lipschitz bounds and the strong convexity, turn out to be slope restrictions or sector bounds, quadratic constraints on the input-output behavior of this function. And you can use that to create analytical proofs of how quickly will my algorithm converge. And then there's some additional work. I think Brian Van Scoy has like the fastest known first order method for converging. And there's been some recent work by Karsten Scherer. In fact, I think he gave a plenary at the CDC last December, just kind of talking about these type of ideas, how control theory can affect the design of optimization algorithms. You can extend this to things like stochastic optimization. So usually if you're trying to do some supervised learning, you might have a cost function like this where n is extremely large. So one thing that people will do, they'll take one of these, maybe this is like one image in a classification problem, compute the gradient with respect to one of these that's chosen randomly, take a step size, and then update and do this again. This is known as stochastic gradient descent, and all these ideas can be generalized to handle things like stochastic gradient descent and prove, rates of convergence in some expected sense. So that was work done by one of my students, Bin Hu, in collaboration with Anders Ronser. So I'll kind of skip over the details there. Okay, so I think I'm basically out of time. So let me kind of get to the conclusions. I know this is a data science, series, and so the point of this talk was to give you a model-based perspective, which is things like aerospace. We use models that are done from a combination of physics and data to design our controllers, but our models are typically extremely low order. They're kind of capturing the essential features of the dynamics, but neglecting lots of things. And so the controls field has developed a lot of different tools to assess the impact of nonlinearities, parametric uncertainties, non-parametric uncertainties. These were the unmodeled dynamics. And these were all part of this kind of general framework. So these quadratic constraint methods that I talked about in the controls literature, that might be called structured singular value or mu analysis, or more recently, integral quadratic constraints. These are kind of the names of the tools. And the point of just the last part is to say that these tools, which were developed for the traditional model-based literature, can be adapted and extended to analyze things like neural networks, optimization algorithms. And so then there's an interplay between now, if I'm starting to do more data-driven, learning-based control designs, I can then maybe merge these two ideas and get maybe a powerful framework where maybe some of the controllers were developed from data, but maybe I can still get stability proofs and proofs of robustness to model uncertainty. So with that, I'll conclude. I'll just kind of leave on a slide of just acknowledging all the funding sources that went into this. And if there's questions, I'd be happy to take them at this point. So thank you for your attention.
Okay, thank you very much, Pete, for your talk. We're waiting actually for maybe if there are any questions from the audience. You can use the chat box in here. If we are able to pick up one or two questions, please go ahead and use the chat box to write your questions so we can ask them to Pete. Okay, quite silent. Okay, so you can read the questions actually. Can you read, Pete?
Yep. Yeah.
The questions? So
Okay, in the panel code for the aircraft, you said you have a local model on a small bit of the airplane and combine it with a finite element model to get the global model. Yeah, the panel code is effectively like if I take the wing and I break it up into little chunks, little plates. Each plate then basically you can model, what's the angle at which the air is hitting that plate. That tells you kind of what the force vector is on that plate. And you can also then model like how is that plate interacting to its neighboring plates. If you break the wing into 1,000 little plates, you effectively get like each plate maybe has 4 or 5 states modeling the motion of that plate. And then, but all the plates are coupled together. So you get maybe 10 or 20,000 states. And so that panel code, I think we've got like a 20,000 state model. That's considered medium fidelity because these plates are not really kind of the way we're modeling the aerodynamics in the plates is not the highest accuracy sort of physics. So that then gets the global model in the sense of like all the plates are interconnected. They're also connected to the fuselage or the center body, so you can then get kind of the rigid body motion out of it as well. But that's a very kind of, I don't want to say it's ad hoc. I mean, there's a long history of developing these models, but it does require some heuristics to kind of model it correctly. So that's the idea.
So other questions from Morgan Jones. Gradient descent has asymptotic convergence 1 over n and instead of 1 over n squared. How does this stability analysis improve on these bounds?
Yeah, that's a great question. So first off, the bounds that you get, I'll say there's two benefits here. One is the analysis itself isn't going to give you better bounds than what are already known, but in this framework, the proofs are extremely simple. Once you know Lyapunov theory and integral quadratic constraints, the proofs for the convergence rates for all of these, which really just recover known results in the literature, like the ones that you mentioned, are very simple. So there's two benefits of this. When you go to the stochastic version, this is really what Bin's thesis was about. He realized that, at the time, a lot of people were doing stochastic gradient descents. There were all these different methods. The original papers on the convergence rates for these were all like 30-page long, extremely long proofs. Then he would recover very similar proofs of convergence in just a few lines because he's leveraging this framework, which is like the analysis that you do for the stochastic gradient descent is actually fairly similar to the analysis you would do for Nesterov's or standard gradient descent. So I think that's nice in the sense that it just gives you one framework to understand lots of different algorithms. The second benefit is once you understand that framework, if I back up the work by Brian Van Scoy and Scher, Mihailo, there's a Taylor, all these people, they understood that once you had this framework, I could start then using this for algorithm design. So it turns out Nesterov's method is not the fastest converging algorithm. If you go look at Brian's paper, he's got a short 6-page paper. He says, "Oh, let's take this. What's the structure of this? Can we figure out a way of then modifying Nesterov's method?" And he uses what's called a triple momentum algorithm. I think my recollection is Nesterov method has 2 states of memory. He adds a third state, and he gets something even faster. And so Carsten Scherer also has some recent results in this. So I would say it doesn't necessarily improve on the bounds that are known. It gives you a framework to analyze lots of different cases within one framework, and then it gives you a method to then analyze or develop new algorithms that actually do give you improved bounds. The next question is, I guess it says,
Go ahead.
oh yeah, go ahead. Go ahead.
You can go ahead. Actually,
okay.
It's fine. It's all right.
It's generally hard to define Lyapunov function that satisfies the stability condition. You have a family of functions. That's true. So what we're doing is somewhat conservative. If you try to analyze the full system with its nonlinearity directly, that would be very hard to find a Lyapunov function. Instead, what we're doing is splitting out linear dynamics, bounding the behavior of the nonlinear dynamics. It's known for the linear dynamics, quadratic Lyapunov functions are necessary and sufficient. But we're still doing something conservative because we're bounding the input-output behavior of the nonlinearities and the uncertainties. How conservative that is depends on the precise problem you're asking. So there are some cases where this turns out to be a very conservative bound, and other cases where it turns out to be actually a very tight bound. So for example, we have a recent paper, ReLU. If you use ReLU as your activation function, the set of quadratic constraints we can write for that encompasses only 2 functions, ReLU and like a flipped version of ReLU. And so in some cases, this is conservative, some cases it's not. But basically, we're relying on quadratic Lyapunov functions. There's a whole literature on using higher order Lyapunov functions, polynomial Lyapunov functions. Those are more powerful, but computationally, they scale much worse than just using quadratic Lyapunov functions.
Next question, actually.
Next question from Landline. Could you comment on safety hard constraints in the non-traditional control methods? I would say this is a matter of still being discussed as a matter of practice, if that's what I take your kind of question to be. If I were to try to do an adaptive controller or a neural network controller, especially on things like urban air taxis, I think they're still trying to work out, I'll put it this way. Traditional aircraft have 2 pilots in the cockpit. Urban air taxis are trying to get to 1, potentially maybe even go down to 0 in the long term. So there's all sorts of questions of like, how are we going to certify things when we don't have 2 pilots in the cockpit? We only have 1 with maybe an AI co-pilot. And I would say at the innermost level, the level that I'm talking about, the requirements are intended to be the same. So the FAA requirements on flight controls, again, have things like you have to be stable over the entire flight operating region. So traditionally, the way this is done is you linearize the aircraft dynamics at a bunch of flight conditions. The controllers are technically nonlinear. They're gain scheduled, but you linearize them also at the operating conditions, and you prove stability in certain margins. The margins here really are just gain and phase margins. You'd prove those at a bunch of operating conditions. So presumably you'd need to do the same thing even if your controller was a neural network. If by hard constraints you mean things like collision avoidance and so on, that's a whole separate set of constraints. Yeah, that could be a long discussion. I could follow up if you have follow-up questions. Next
Last
question
actually from Ross.
So from Ross, if the neural networks are used to generate a reference, then the problem may become incremental stability. Yeah, so the incremental stability. So I should say the L4DC, the Learning for Dynamics and Control conference, was in Michigan just this last week. So if you search L4DC in Michigan, I'll give maybe a little bit of publicity to them. I gave a tutorial workshop the day before with Ian Manchester and Bin Hu on neural networks, both for things like image classification and in the feedback loop. And the connection there is, generally speaking, the Lipschitz constant for the neural network. You'd like that to be small so that the input-output behavior, in an incremental sense, in the way that you're asking, Ross, is you'd like that to be small, because then that'll, in all sorts of problems, in image classification and the feedback loop, that'll make you more robust. You'll be more robust to pixel error if you're doing image classification. You'll be more robust to model error if this has got a small Lipschitz bound. But those turn out to be incremental stability problems. The short answer is yes and no. The incremental part, you're really using slope constraints on the activation functions to then in the incremental setting, you're basically getting to a version of sector bounds, which are, I think what you're saying, kind of circle criterion. So I was actually asking Ian about this. Are there other versions of this that are stronger for the incremental case? Because we've got a recent paper on ReLU where we've got incremental constraints that are not just for ReLU, not just the circle criterion. That's a paper with myself and Ger Delarud. Sahel Vahidi Nouri is the student on that. It's on arXiv right now. So the short answer, I guess, for the incremental case is it depends on what the specific activation function is. At least for ReLU, I can tell you, yes, there are less conservative ones.
All right. I think actually we are done. So with all the answers provided actually by Pete, I don't have time actually to ask my questions, but thank you very much, Pete, for coming actually today and joining actually to deliver this talk. So I'll be pleased actually to see you actually soon for other events actually together we could organize together. So thank you very much all for attending, and see you actually for the next talk series. Yes. Thank you.
Yeah,
Bye-bye.
thanks again for the invite. If people have questions, feel free to email me. I'll also be
Yes.
at the European Control Conference this summer. So if anybody's there, I'll see you there in Greece.
Thank you very much, Pete. Thank you. Thank you, the audience. Bye-bye.
Thank you, everyone.